What is haptic? By definition, haptic technology is a tactile feedback technology or a touch sense technology. Haptics is the interaction between humans and the virtual world in the sense of touch. Haptics is adding the sensation of touch to the computers. Haptic feedback allows a user to interact with computer-based devices by receiving tactile and force feedback. The former may let us know what is the texture of the object. The latter simulates some physical properties of the object, such as its weight or pressure. Tactile feedback encompasses haptic sensing, but also feelings at the surface level. Force feedback, the simulating of physical attributes such as weight in gaming and virtual reality, allowing the user to interact directly with virtual objects using touch. History of haptics. One of the earliest applications of haptic technology was in large aircraft that use servo mechanism systems to operate control surfaces. Such systems tend to be one-way, meaning external forces applied aerodynamically to the control surfaces are not perceived at the controls. The first U.S. patent for a tactile telephone was granted to Thomas D. Shannon in 1973. An early tactile man-machine communication system was constructed by A. Michael Knoll at Bell Telephone Laboratories Incorporated in the early 1970s. And a patent issued for his invention in 1975. In 1994, Aura Systems launched the Interactive EST, a wearable force feedback device that monitors an audio signal and uses Aura's patented electromagnetic actuator technology to convert bass sound waves into vibrations that can represent such actions as a punch or kick. In 1995, Norwegian Geir Jensen described a wristwatch haptic device with a skin tap mechanism, termed tap-in. It would connect to a mobile phone via Bluetooth. Tapping frequency patterns would identify callers to a mobile and enable the wearer to respond by selected short messages. Nowadays, haptic technology is heavily invested and researched as to improve the virtual world experience that is integrating to our life. The first generation uses electromagnetic technologies which produce a limited range of sensation. Second generation touches coordinate-specific response, allowing the haptic effect to be localized to the position on a screen or touch panel, rather than the whole device. Third generation delivers both touch coordinate-specific responses and customizable haptic effect. Fourth generation focus on pressure sensitivity. For example, how hard the force exerted on a flat surface can affect the response. These are the main components of a haptic feedback. Touch screen to detect touch pressure and send signal to the processor. Processor that generates specific waveform according to the touch. And actuator to create movement according to waveform by processor. This is the block diagram of haptics. First, the touch screen controller sends a trigger signal to the processor when a press is detected. Then the touch event triggers the processor to generate a waveform. Finally, the waveform causes the actuator to move in a specific direction or pattern to create a vibration. These are the 5 main types of haptics: the force feedback, vibrotactile feedback, electrotactile feedback, ultrasound tactile feedback, and the thermal feedback. Haptic force feedback is the kind of haptic feedback that appeared first. Therefore it is the most studied. Force feedback affects the ligaments and muscles through our skin into the musculoskeletal system, whereas all other types of haptics devices that affect only on our skin receptors. Generally, other types haptic devices that affect the top layers of the skin are called cutaneous devices. They are quite compact and act pressure on small areas of the body. By contrast, force devices are large, as a rule. They move together with a human and have an impact on large areas of the body such as an arm or a leg. These haptic devices are more complex as they have to provide a person with sufficient freedom of movement. Two kinds of force feedback devices exist: biomimetic and non-biomimetic. Biomimetic devices move as human limbs and resemble them by their forms. Such devices are difficult to develop because ideally they should have a functionality of human body and be suitable for different people. Non-biomimetic devices may be very different from the human body. All force feedback appliances may be divided into resistive and active ones. Resistive devices limit the movement of the user with the help of the brakes. Active devices restrict movements of the user or move the body in space by means of motors. Active haptics devices can simulate a wide array of interactions, but they generally need to be more powerful than passive devices, and they are more difficult to control. Vibrotactile feedback is the most common type of haptics. Vibrotactile stimulators apply pressure to definite human skin receptors. These receptors look like onions and can pick up vibrations of up to 1000 Hz. Ordinary human speech frequency varies from 80 to 250 Hz, so our skin is able to feel sounds. Vibrotactile feedback is relatively simple, cheap technology, easily powered and controlled. It has long been used in many devices like mobile phones, joysticks, steering wheels. Vibrotactile feedback requires fewer tracking parameters and quite small power consumption. However, vibrating motors cannot provide depth and diversity of sensations. Vibration may sometimes be irritating in comparison with other stimulators. Vibrating motors are hard to miniaturize efficiently. In addition, if used long enough, vibrotactile feedback caused deep penetration, negatively affecting ligaments and joints. Furthermore, ghosting effect may appear with prolonged or strong impact. Electrotactile stimulators affect not only receptors but also the nerve endings with electrical impulses. As a result, a person wearing the haptic suit based on electrotactile feedback technology can feel the texture of an object or feel a breeze, for example. In fact, almost any sensation may be simulated with electrical impulses. This type of feedback has many forms depending on the intensity and frequency of the stimulus delivered to the wearer's skin. Sensations can also vary depending on the current, voltage, material, form of the wave, electrode size, contact force, hydration and skin type. Electrotactile feedback has great potential because with its help haptic effects can get a diversity of forms. The principal advantage of the electrotactile haptic feedback system, compared to vibrotactile or force feedback, is the absence of mechanical or moving parts. By means of electrical impulses, a user is able to receive a wide range of sensations which cannot be reproduced with any other feedback systems that currently exist. One more benefit of electroneural stimulation is that the electrodes can be customized into compact arrays and used to implement electrotactile displays. Electrical muscle stimulation or EMS is used in medicine for more than 30 years and has proven its safety. Moreover, electrical signals are the basis of the nervous system, so we can say confidently that this type of feedback is better suitable for generating and simulating sensations. Ultrasound is a sound wave of high frequency. One emitter or some of them are used to create ultrasound feedback. One emitter located on one part of the body may send a signal to another part. This principle of transmission is called acoustic time reversal. To ensure the impact on larger areas, it's necessary to form a haptic feedback field. Each emitter itself is not powerful enough to do it, so several emitters are used. Together they create invisible tangible interfaces in the air. Ultrasound waves generate turbulence which one can feel through the skin. The main advantage of ultrasound technology is the user do not need to wear any accessories. But this kind of haptic feedback is quite expensive and usually less perceptible than vibrotactile or electrotactile feedback. For thermal feedback formation actuators, grid is used. It is in direct contact with the skin. There is no need in a large number actuators to create a heat feedback, and they can be positioned not so close to each other. Thus, in some way thermal feedback devices are easier to design. However, due to the law of energy conservation, heat cannot be taken from nowhere. It can only be moved from one place to another. Furthermore, it should be done quickly to provide a realistic feel. So, haptic suits using thermal feedback require quite a lot of energy. Application of haptic technology include medical application, entertainment, mobile phones, games, robot control and holographic interaction. Haptics has its advantage in improved working style, communication between real world and virtual world, and increased confidence in medical field. However, there's also disadvantages in higher cost. Touch with very high precision requires a lot of advanced design.
Haptics is the science of touch. It's how we interface with the world in many aspects, and ultrahaptics is about how we create that sense of touch in midair. So we can create buttons and sliders and switches, or even virtual objects in midair that you can touch that really don't exist. How we do this is by using ultrasonic transducers, an array of them, where we can change the amplitude and phase of all the transducers individually, which means that we can bring all the sound waves to a single point at the same time, which creates a high pressure level that you can feel on your skin. Now, the skin can't respond to ultrasonics. It only responds to frequencies of 0 to 500 hertz. So we modulate the ultrasonics at a frequency around 2 to 400 hertz, which creates a sense of touch. Now, if you touch a surface, you don't feel anything, but if you slide your hand across it, you can feel the texture of that simply by the vibrations that come off that piece of material or that piece of wood or whatever you're touching. And we can recreate that in midair by how we modulate the ultrasonic technology. And so it allows us to create not only the sense of touch, but a sense of texture, and able to recreate things that you wouldn't normally be able to recreate.
This box sends ultrasonic vibrations into the air so that you feel objects as if they were hanging in thin air. Now, what we're going to do is try and guess some shapes here, okay? Now, this is actually going to create a noise, so we can't talk whilst you're trying to guess that shape, okay? Right, so what we're going to do is put the picture on the screen so everybody else can see it, and then I want you to guess if the object is either a cone or a square. Okay, so they are your two choices. Okay, are we ready? Right, so let's just...
Is it a cone?
Say that again.
A cone.
We think it's a cone. So can we see? Yeah, and that's what everybody else can see. It's a cone. Excellent. Well done. Well done. So what we have are 256 tiny speakers, and they're creating ultrasonic vibrations. So they're outside of the human range of hearing. So we can't hear them, but Ethan can feel them. And it's like that feeling, you know, when you're near a very loud bass speaker, so you can feel it in your chest. So it's like that, but much, much more precise.
In summary, haptic technology is the technology that brings us seamless connection with the virtual world with sense of touch in the future.